Hello there and welcome back. Today we're going to be introducing a numerical technique that is often used to solve at least basic optimization problems, and that is called the Newton-Raphson iteration method. So the goal of the Newton-Raphson iteration method is well, there's usually two goals that the Newton-Raphson is used for, but the first that we're going to be focusing on is to optimize some functional. In the realm of statistics and regression, for example, a function that we often minimize is usually the error sum of squares, right? Which is the sum from k is equal to 1 to p, or the sum from k is equal to 1 to n of our y value minus the predicted y value, y hat k, where y hat k has of the form beta 0 plus beta 1 x1 plus beta 2 x2 all the way down to say beta p xp. So these unknowns, beta 0, beta 1, beta 2 down to beta p, of course have a closed form representation in terms of the minimization of SSE. In particular, you can find that beta is equal to xtx inverse times xty in the linear algebra form. But of course, not all functionals have a closed form representation in terms of the solution, whether we be minimizing or maximizing or some combination thereof. Okay, so we're just going to be focusing on the univariate optimization problem. In particular, let's assume that we just have one unknown variable in our functional that we seek to optimize. And of course, later on, maybe we'll discuss how to vectorize the Newton-Raphson method and possibly even go into more advanced numerical techniques that can optimize multivariable problems. So let's just use a very basic example to optimize. And let's choose the polynomial p of x is equal to negative 0.3 x to the power of 4 plus 3x plus 4. So if you may remember how to graph this from pre-calculus, at least to some degree, you should know that the graph of this function is going to have a shape similar to this. So our goal is to find the x value associated to this maximum value of p, i.e. we seek to optimize this function. So let's just lay down a couple basic calculus principles that the Newton-Raphson method is sort of based on. So 1, p of x is maximal if 1, the derivative at that point is positive, i.e. if you draw a tangent line to that curve at that point, it will be a horizontal line. And that's not the only requirement. 2, the second derivative at that point must be negative, i.e. it must be concave down at that particular point. And if we want to minimize, then a couple things should be true. So p of x is minimal if 1, again, the derivative is 0, but the second derivative at that point is positive. Okay, so if you sort of draw another curve, for example, a parabola, notice that that, of course, has a derivative equal to 0, but it is convex or a concave up function. Okay, so we're going to assume just a couple basic things about the function that we're optimizing here. The first thing is that there exists only one value x that optimizes this function. We're not going to be going into how to test whether it is a maximum or a minimum, so maybe you can use some graphing software to sort of get the basic intuition of the functional that you're actually working with. For example, the least squares regression problem, one can easily show that that problem actually has a unique minimum. So when we minimize that multivariate functional SSE, whatever the vectorized Newton-Raphson method converges to will, of course, be a minimum value for that particular functional. So let's assume that we know as much of about this function p of x as we do, for example, the SSE, in particular that it has a unique maximum. So whatever value the Newton-Raphson method is converging to, we will know, let's say, it is a maximum value. So let's briefly go into what the Newton-Raphson does and how it does what it does. Right? So let's draw our polynomial p of x, which has this type of shape. And let's assume that we're interested in graphing the derivative of this curve. So keep in mind that the x value for which it has a maximum is going to be there. And if we want to sketch the derivative of this, notice that the slope of the curve is positive everywhere to the left of that point. So the derivative of the curve is probably going to look something like this. So this blue curve is going to represent p, and this green curve is going to be represented by p, p prime, or the derivative of p. So now, if we focus just on the derivative of p, and let's sort of stretch the curvature of that just a little bit so we can get a nice graphical understanding of what's going on here. So our goal is to find the zero. So our goal is to find the zeros of p prime, which is the same as finding the optimal values of p. So how does the Newton-Raphson method, how does it do what it does? So what we're going to do is we're going to do an initial guess. Let's call it x0. And then we're going to plug that initial guess into the derivative of the function that we're trying to optimize. That's going to give us some value over there. And then what the Newton-Raphson iteration does is it finds the derivative at that point. So that would be the second derivative of p. And then it uses the x-intercept at that particular point. And then I need to sort of change my function so it doesn't sort of dive off. And what it does there is it plugs in that particular value and it finds the derivative at that point. So this blue point, that's going to be x1, and then where this teal point crosses the x-axis, that's going to be x2, and then we're going to plug that value in, and that's going to give us another horizontal line. That's going to be x3, and as long as your initial guess was, pretty good, I'm not going to go into the theoretic details of that, it's more of a numerical analysis question, it should be converging to the zero of the derivative of p. So that's pretty much what's going on there. So let's sort of sketch out what's going on here. So the Newton-Raphson method. So the Newton-Raphson iteration starts off like this. So we're going to let x0 be an initial guess. So if you have some intuition of where the optimal x value is located, definitely choose somewhere around there. And then xk plus 1 can find from the geometric picture that I've drawn, is actually going to be equal to xk minus f of xk all over f prime of xk. So this f function that's being referenced here, f is the function you want to find the zeros of. Or you can represent this from the optimization approach. So this is equivalent to xk minus p prime of xk all divided by the second derivative of p evaluated at xk. Here p is the function you want to optimize. All right? Now that we have laid out at least what the Newton-Raphson iteration does, let's actually get into a discrete computational method that we can use to approximate the first derivative and the second derivative of some function that we seek to optimize. So in case you don't remember some things from your first semester calculus course, remember that the definition of a derivative is commonly presented in this first little blue box, which is sometimes referred to as the forward difference definition of the derivative, and that is the limit is h approaches 0 of f of x plus h minus f of x over h, and you can approximate the derivative of a function f at x if you just replace h with an arbitrarily small number and just ignore the limit. Now, that is not the only definition of derivative that exists. Actually, if f is differentiable at some point x, then you can also use this definition on the right as well. This is referred to as the backward difference. So instead of looking towards a point in the future of x, you can actually look at a point in the past of x, and that will actually give you the same exact result. Both in terms of accuracy, the forward and difference produce the same results as long as h is the same exact value. But there's actually an approximation that is even more accurate than the forward and backwards difference approximation for the derivative, and that's this one in the purple box. This is known as the central difference approximation, which you can arrive at by taking the average of the forward and backwards difference, right? And you can sort of see that here. That's the future, that's the past, and that too comes from the average of these two values, right? And these all three produce the same exact result analytically, and in terms of approximations, all you need to know for now is just the central difference technically will be more accurate for a given fixed h value. Now, what we're going to do is we're going to approximate the derivative of our functional p, and we'll also need to approximate the second derivative of our functional p as well. So let's state the limit definition of the second derivative via the central difference. So the central difference for the second derivative of a function. And if you want to sort of dive into the theoretical nature of the convergence and the stability and all those fun little things, that would be more of a numerical analysis audience, in case you sort of want to check that out. But for now, we're just going to present these methods because we need to use these for some optimization problems, for example, in statistics or something like that. So the second derivative of a function f can be approximated, so the limit as h approaches 0 theoretically, of 1 over h squared of f of x plus h minus 2 f of x plus f of x minus h. And that's the central difference approximation for f double prime. Now let's switch this into our Newton-Raphson setup. So remember, what we're going to be interested in is we're going to be interested in the expression p prime of xk divided by p double prime of xk, right? Because remember, we're going to have an xk minus this expression, right? So what is that expression going to be equal to? So let's sort of do the math out. So that's going to be equal to 1 over 2h of f of x plus h minus f of x minus h all over 1 divided by h squared of f of x plus h minus 2 f of x plus f of x minus h. And then that quotient term here, let's just call that quotient term q. That means q will be equal to, so notice these h's cancel, that 2 is going to go to the bottom and that h is going to go to the top. Once you keep change, flip those fractions. And we're going to have h divided by 2 times, on the top, on the bottom we're going to have f of x plus h minus 2 f of x plus f of x minus h. And then we're going to have f of x plus h minus f of x minus h on the top. And that will give us a expression that we're going to replace in our Newton-Raphson iteration, and then we should be able to optimize any functional p for which we're going to be interested. So now that we have the theoretical things already set up, let's head to R and implement this and do a couple examples of it. So the first thing that we need to define is our initial guess. So what is our initial guess going to be? So as long as our optimum is unique on our interval, we shouldn't be too worried about our initial guess, and technically we also assume that our function is relatively not a flat function. If you look at the geometry picture, you might be able to come up with a couple examples of where the Newton-Raphson iteration actually does not converge to a unique solution, or doesn't converge at all. So not relatively flat, and a unique optimal value is usually the two minimum requirements that we have for the Newton-Raphson method to converge to a unique value. So our initial guess, let's actually call it xk, and let's actually just let xk to be equal to 0. That's a safe thing to choose, especially if you know that it could be slightly negative or slightly positive or something along the lines. Let's also define the number of iterations, because we don't necessarily want this thing to run forever. You could also do, for example, a while loop and sort of stop the iterations if you reach a certain convergence error or something along those lines. And let's actually call this n iter for the number of iterations. Let's call that 100. Right, let's define that and define that. Now let's define our function. Now we could create a different file, sort of like we have before with our LU decomposition, our SVD or skewness function or Nemo LM function or something on those lines. But we can actually define an inline function in our local environment so we don't have to create a new file. As long as our functions are small, this is generally a good thing. Let's call it my fn from my function. And this is going to be a function of a single variable. Let's call it x. And what is this function going to be? So our function is going to be p is equal to negative 0.3 times x to the power of 4 plus 3 times x plus 4. So this is the function that we're trying to optimize. And then we're going to return the value of p once we give it a value of x. Okay, so once we run that, then our function sort of comes up there, that means our function at least is well defined, and then we can call it a little bit later. Right. So now let us write our Newton-Raphson method, and this is the code for a one variable or one-dimensional Newton-Raphson iteration method. So the first thing that we need to do is define our h. You can make your h super small if you really want to, but generally it's safe to not make it super close to 0, as you're going to have a dividing by 2 error, because remember, we're doing h squared in the denominator of our second derivative, and of course that's smaller than h. So try not to get too carried away in terms of the precision, because the more and more this iteration converges, it should be converging to the exact answer provided all as well, right? So as long as h is super small, you shouldn't need to worry too much, but that's more of a numerical analysis discussion. So for k in the interval from 1 to the number of iterations for which we want to carry out, so the first thing that we need to do is calculate our derivative ratio. Actually, let's just call it q to make things nice. So remember, we came out to h over 2 times our function, which is called my function, evaluated at our initial guess plus h, and then minus our function of our initial guess minus h. So that's the top, divided by my function evaluated at our initial guess plus h, minus 2 times our function evaluated at our initial guess, and then plus our function evaluated at xk minus h. That's our quotient. And then our x new value is going to be equal to our old x value minus that quotient value. Let's print the value that it's calculating so we can sort of see how fast it is converging. And then once we're done with that value, we need to update our initial guess. So replace the old xk with that new x value, and then continue that until we're sort of happy with everything. So let's of course just make sure everything is running well. So define those things, define our h, and then when I run this next line, it should give us all of our approximations. So notice our first iteration. So remember, our first guess was 0, then it goes to 50,000, then 33,000, then 22,000, and then it gets closer and closer to this number 1.357184, which you can find via, for example, a calculator or a graphing calculator. This is the exact value of the maximal value for that function that I did graph before. So we see that our Newton-Raphson method does converge quite nicely. Now keep in mind, our implementation here is from the optimization perspective. So if you want to solve this problem from the zeros perspective, you will have slightly different results in these first couple of iterations. In particular, it probably will converge a lot quicker than the optimization approach, because keep in remember, we're approximating the second derivative and the first derivative instead of just approximating the first derivative, which is the zeros approach. But usually the optimization approach is sometimes a more efficient method from the practical coding perspective, because we usually do not know the derivative representation of that, or the derivative representation of that might not be the nicest to sort of get. Right? So from the practical perspective, the optimization is perspective, but from the analytical numerical convergence perspective, it might be a little, downside, but as we see, it does eventually get to the correct solution. As long as you run, for example, like 20 iterations, it gets to the exact solution pretty quickly, even if we're doing this from a more higher level approach. As a closing example, let us assume that we want to approximate the value of the square root of 5. I already know that the function is already implemented in R, so you could easily find the square root of 5 by yourself without having to write a program for it. But there are some programs and functions that might not be already pre-implemented in the R programming language or maybe in some other libraries that you may need to find the values of and also analyze in terms of plots or something else. So the Newton-Raphson method actually provides a way of evaluating particular functions as long as you know some other functions that are related to the function that you're working with. So for example, if we're interested in finding the square root of 5, if we want to use the Newton-Raphson method, of course, this is designed for finding the optimization of that particular functional or finding the zeros of some other given functional. So if we think about the square root of 5, we know that x squared minus 5 is a function for which square root of 5 and its negative are zeros of it. So if we think about a function whose maximum or minimum is the square root of 5 or negative square root of 5, then we can simply just do the antiderivative of that particular function. For example, 1/3 times x cubed minus 5x plus some arbitrary constant. Let's just assume it's 1. So what I want to do is, of course, I want to block out this old function because that's not what we're actually focused on. And we already know the square root of 5, but let's pretend that we actually don't know what it is. Now, our initial guess. Think about this for a moment. The function x squared minus 5 has a minimum at x is equal to 0. So if we use 0 as our initial guess, that's going to give us a horizontal tangent at x is equal to 0. And a horizontal tangent that isn't a horizontal axis never actually crosses the horizontal axis because they're parallel lines. Therefore, x k plus 1 is going to be an infinite quantity, so the Newton-Raphson method will not converge for initial guesses is equal to 0. And you can, of course, try that on your own if you want. So if you want this to converge to the square root of positive or the positive square root of 5, you have to choose a number bigger than 0. I'm not going to go into the theoretical proof of why that is the case, but if you choose any number less than 0 for your initial guess, it's going to converge to the negative square root of 5, in case you're interested in exploring that. So let's define our initial guess, the number of iterations, and the function that we're actually going to try and optimize here, in this case 1/3 x cubed minus 5x plus 1. Define your h value to be something small but not super small, and then run your Newton-Raphson iteration method, and that gives you a bunch of approximations for that particular value. Of course, notice that the first iteration is going to be the most inaccurate of them all. 25 is definitely not the square root of 5 because the square root of 4 is equal to 2 and the square root of 9 is equal to 3. So the square root of 5 should be some number between 2 and 3. But eventually notice that it does converge to at least approximately what the value should be, which is 2.2360601, which we can of course cross-reference with R's value, which is really, really close to that particular value, right? So the Newton-Raphson method is actually a weaker version of what R actually uses to calculate the square root of 5, which is actually pretty nice. But that is the Newton-Raphson iteration method and how it can be used to optimize a univariate function or find the zeros of a univariate function in case that is something that you need to do in your practice. There is a multivariate version of the Newton-Raphson iteration method, where you can, for example, find the least squares estimates, for example, beta 1, beta 0, beta 2, beta 3, beta 4, beta p if you really wanted to. That would be the vectorized version of the Newton-Raphson iteration method, but we're not going to get into that today, but maybe you can sort of play around and see if you can vectorize this particular 1D Newton-Raphson iteration method, but it's a little bit more tricky. I'll just give you a heads up on that. But for now, we'll just say goodbye, and we'll see you in the next video. Take care.